which is 0.997. So what you may notice from the proportions or the decimals is that if you add these up, they add up to 1, or 100%. Whenever we construct a probability distribution, this is sort of like a new type of sample space. So in any valid probability distribution, all of the probabilities have to add up to 1, because something will happen. One of these will occur. Some are more likely than others, but something will happen, so the probabilities have to add up to 1. So what we need to do next is we need to figure out this, on average, how much money are we giving to each customer? So what's actually happening is one person gets 10,000, two people get 5,000, and the rest get 0. So we need to figure out in total what's being paid out. So what we'll do is we'll imagine that we have 1,000 numbers. 1,000 spaces to fill, and those signify or represent our customers. So each customer is going to receive some amount of money. So we know that one of those will get $10,000. Two of them will get $5,000. And then the rest get 0. So we have to draw 997 zeros. So we have a big list of 1,000 numbers. Almost all of them are zeros, but we have two 5,000s and one 10,000. So our total payout, we add up all the money we're giving away. We can ignore the zeros, so we're left with 10,000 plus 5 plus 5,000. So in total, we expect to pay out $20,000 to our customers. So now what we want to do is we want to split this up evenly across every customer. So what that gives us is the average amount we're paying back. It's not actually what we're giving them, but it's what we expect to give each person. So we compute the average. So we take our total, we added everything up, divide by how many numbers we had. We're assuming 1,000 customers. So that leaves us with $20. So what this is telling us is that when these people give us a policy, when they give us money for their insurance, on average we're expecting to give each person back $20. And what that works out to be is that really one person's getting 10,000 and two people are getting 5,000, but we're just spreading that out evenly across all the customers. So each person gets $20. That's what we expect to have to give back. So now we can answer the question. We want to make $50 per customer. We know we have to give them back $20. So our policy, the cost of the policy, we know we're giving them 20. We want to keep 50. So we need to charge each person $70. Each person gives us 70. On average, we'll give them back 20, so we keep $50 per person. And that funds the 1 out of 1,000 who dies and the 2 out of 1,000 who are disabled. So this table is just a summary of data of 1,000 numbers. It's a frequency table, basically. But since we're focusing on something probabilistic and reporting relative frequencies, it's a relative frequency table, but we just call it a probability distribution. We can find this average, the $20, in a different way. We don't have to have all 1,000 numbers. All that we need is the table. So another way to compute the average is you take each little x, each quantitative value, multiply it by its probability. So you'll do that for each pairing, and then you add up all of those products. So we start with the first one. We'll do 10,000 times 1 out of 1,000 plus the next one, 5,000 times 2 out of 1,000 plus the last one, 0 times 997 out of 1,000. So this one gives us 10. 10,000 divided by 1,000 is 10,000. 10,000 divided by 1,000 is another 10. 0 times anything is 0. So again, we get 20 bucks. And we could compute the policy cost from there again. So we'll show this in a couple of pages, but this computation here is basically saying it's basically a shorthand form of our 1,000 numbers. It's saying that one of your 1,000 numbers is a 10,000. Then you add 2 5,000s out of your 1,000 numbers, plus 997 zeros out of your 1,000 numbers. And we end up with the same result. So there are two ways to compute an average from a probability distribution. We will use this shorthand way, and we'll do that more later. The probability distribution itself is just these bottom two rows. These bottom two rows. So it's going to be the quantitative measurement and its probability. We'll ignore the qualitative part. So let's do another example. Okay, so there are 26 letters in the alphabet, 21 of them are consonants and 5 are vowels. So what we're going to do is put each letter on a piece of paper, put it in a hat, and we're going to draw 3 of those slips of paper at random with replacement. And what we're measuring is big X. So that's our random variable. That's our event of interest. That's the thing we're interested in. So what we're measuring is how many consonants did we draw. So in earlier examples, in earlier chapters, we would say X equals height. It's just an abbreviation for what we're measuring. Here what we're measuring is something a little odd. We're counting the number of consonants that we see on our 3 slips of paper. So big X, that's our random variable. That's the number of consonants. And then we have little x. Little x denotes what are the values that we could see for this random variable. How many or what possibilities for the number of consonants could we see when we draw 3 slips of paper? So you could have 1 consonant in your 3 slips. You could have 2. You could have 3. And the one that's often forgotten is 0. You could have all vowels. 1 could be a consonant, 2 could be a consonant, or all 3 could be consonants. So we've defined our random variable. That's what we're measuring. We're counting things typically, and that's the number of consonants. And then the little x, those are the values of that random variable that we could see. We don't know which one we'll get, but each of these could happen. So now what we want to do is create the probability distribution. So we have 2 rows or 2 columns. I typically draw it vertically. So we have little x, and then we have the probability that big X equals little x. So we write down the values that we could see. And then the column on the right is saying, what's the probability that your random variable, the number of consonants we see, equals each little x? So this spot here is saying, what's the probability that big X equals 0? What's the probability that the number of consonants you see that you draw in your 3 slips of paper is 0? So we have to figure out that probability. This one is saying, what's the probability that the number of consonants you see is 1? What's the probability the number of consonants you have is 2? What's the probability the number of consonants you have is 3? So, as we think about this problem, it's sort of like the marbles in a jar problem. We have 3 slips of paper. And we have to think about what the possibilities are. So for each one, it could be a consonant, which we'll call C, or it could be a vowel. So we'll call that V. So let's start with 0. We have our 3 slips of paper. We want to know what's the probability that we have 0 consonants. Well, if none are consonants, then that means we have 3 vowels. So our slips of paper will be vowel, vowel, vowel. Like we saw in the marble problem. Oops. There's an and between each of these. So what we're saying is we draw a vowel, we put it back, and we draw a vowel, we put it back, and we draw a vowel. So we want to know what's the probability that we see this outcome. So in the problem we were told we're doing selection with replacement. So from this we are allowed to assume independence. So that means whatever our first slip is, consonant or vowel, it doesn't affect any subsequent slips. We put it back, the hat stays the same, all the slips of paper are as they were before, so whatever we draw next is still random. The probabilities don't change, what we observe doesn't affect anything. So to find this probability, we need to now know what's the probability of vowel and vowel and vowel. So we reach into the hat. What's the probability that the first slip of paper we pull out is a vowel? Well, there are 5 vowels out of the 26 letters. We put it back. What's the probability that the second one is a vowel? So this and is a multiply. It's still going to be 5 out of 26. And what's the probability that the third is a vowel? We put that slip back, we shake the hat up. There are still 5 vowels out of the 26 letters. So, multiply that out, and what you end up with is 125 over 17,576. So this is the probability that you have 0 consonants, or in other words, 3 vowels. Not very high. 125 out of 17,576. Okay, we can do this a similar process for when x is 3. So when x is 3, this is saying we have 3 consonants. So we want to know what's the probability that we get a consonant and a consonant and a consonant. Okay. So we see the ands, we're going to use the multiplication rule. And since we know that these 3 different slips are independent, we just multiply the probability of each of them all together. So we reach into the hat. What's the probability that the first slip of paper we pull out is a consonant? Well, there are 21 of those out of the 26 letters. Put it back, shake up the hat, and what's the chance that the second one is also a consonant? Well, it's still the same. And these are being multiplied. And the same goes for the third slip. They're all 21 out of 26. So when you multiply that out, what you end up with is 9,261 out of the 17,576. Okay. Now, when we get into the middle of the distribution, when x is 1 or x is 2, we have to be a little more careful. So let's start with when x is 1. We have to think about what would our 3 slips of paper look like. So this is saying you have one consonant in your 3 slips. That's it, just one. So we could have the consonant and then a vowel and then a vowel. But that's not it. There are other ways, other combinations that give us one consonant. So we have an or. Or we could have vowel, consonant, vowel.